we're troubleshooting and weren't thinking about things properly. And we've seen the problem with the shift, right? BP America, right? When one shift is not, you can't, it's hard to brief the second shift of everything that has been done unless it's very well documented. And so a lot of times things happens when you either try to start up an equipment or when you're troubleshooting, right? And that's when you have to be extra careful and try to think of everything and anything, right? What could possibly happen? So this is another, right, release where you have an accidental release that's right, workers are just going to be overexposed, and in some instances there are fatal exposures, right? The other part is when we have an accident, and how does that affect the community? So I don't know if you heard of the explosion in the warehouse and the storage facility in China, I can't even pronounce the name, last year. So this was in August, and they do believe that they found the cause, which is the nitrocellulose that was supposed to be stored wet. Well, the water evaporated and by the heat, and it ignited, and of course they stored a whole bunch of other. This was a storage facility where they basically took money to store your hazardous material. Okay? And there what was the latest I was reading? They had arrested 49 people, and they were charging 100 more or something like this. It's a very corrupt place, I guess, is the bottom line, right? They just ignore safety, right? So a lot of companies would take their hazardous waste in here, I'll pay you and you dispose of it, and I don't want to know what you do with it, because they store it in it. Look, did you see all these tankers of stuff? Yeah. Who knows? This is a cocktail. And they do claim, right, that it has a fairly limited impact on the local environment. So they had sodium cyanide in there, and they claim that there hasn't been any death associated with that. Most of those, you saw 110 out of the 165 people who died were first responders. And it's because they responded to the first fire, which was the nitrocellulose, but that later ignited the ammonium nitrate, and that's how they died. If you remember the West Fertilizer explosion, where they were filming the fire and then it exploded. I'm kind of looking at this fairly limited impact on the environment. Yeah, it sure looks like it, doesn't it? Now, of course, this is fish, and this is from the same area, right? But whether or not these fish could have died from the shock wave, right? They don't necessarily, it may not have been chemical poisoning. But I think the bottom line is that we don't really know the truth. We only know what the Chinese government wants us to know, right? So. Bottom line is that, when something happens, this is in northern Spain in February of last year, right? This huge vapor cloud of something toxic. It came from an explosion at a site that was because two incompatible chemicals came in contact. And, it's affected the community down the stream. The Chevron fire in Richmond, California, that toxic cloud, it's not necessarily local to the plant, right? If we have something happening at a chemical plant, it can affect the community. And obviously Bhopal rings a bell, right? So what we're gonna look at is if something happens like this, we have an explosion, we have a fire. Problem with fires in refineries is that you can't put them out. They burn until the fuel runs out. So it can look like this for days, right? And you will have to evacuate the people downwind of the facility. The question is, how far downwind do do you need to evacuate? What is the, right, what's the distance? And it of course depend on a few things. So we're gonna look at how can we estimate that? If we have an accident, right, or which leads to either an explosion and an instantaneous release, or something that will burn for days, so it's more like a continuous release. What will the concentration downwind depend on? So we have to look at those two cases separately. So it will either be a plume or a puff, right? And of course, it's gonna, the concentration downwind, the concentration far away from the plant is gonna depend on where's the wind blowing, because that's where it's going. Keeping in mind that that could change at any time, right? It's going to be, and then of course the concentration will depend on how far away you are from that site. But in addition to the wind speed, so wind speed can do two things, right? First of all, it can transport it faster if the wind is going that way with very little turbulence this way. Then you're getting a higher concentration downwind because it goes faster before it can actually dissipate, right? But in certain areas, a higher wind speed can actually be beneficial because it creates turbulence and it will mix it up and disperse it faster. It also depends on the atmospheric stability. We're going to look at what that means. And the ground conditions, so that basically the ground conditions really mean, right, what are we? Do we have an open field? Or do we have a city with high rises? And there are two things to that, right? It depends on the height of the release. There is a reason for why, you know, chimneys on incinerators are several hundred meters high sometimes, maybe not several hundred, but they're really high, because the higher you release it, the longer it takes before it reaches the ground, and the more time it has to dilute. So the concentration on the ground is going to be lower, right? And then it depends on the momentum, right? Is it coming out at high pressure straight up, right? Because then you're basically increasing the effective height of the release. And then is the gas that you're releasing lighter or heavier than air itself? And of course that depends on a lot of things, right? That depends on a little bit more than just the property of the material, it's temperature too, right? So, but let's look at the atmospheric stability first. What does that mean? So we want, in this case, we want it to be unstable, because if it's unstable, then we have a lot of vertical mixing, and that happens during the day. It's hot on the ground, hot air rises, but then as it goes up, it cools down. So it comes back down, right? It cools down, it gets heavier, and you have circulation that way. At night, you have a temperature inversion. And basically, it's like you're putting a lid on your release. And it cannot, you have limited vertical mixing now, which means the concentration on ground is going to be much higher. And then ground conditions. Again, it's all about vertical mixing. We want it to mix this way. So if you have a lot of high rises, if you have an urban thing or a lot of high rises, you're actually creating turbulence this way. Versus if you're in a rural community or where it's flat, then you have a lot less disturbances, right, that will actually cause vertical mixing. And of course it depends on the wind in all of these cases. Height of release. So again, this is the reason, right? It's if it releases, if you also have a little momentum going up, right? You're increasing the effective height. It's going to keep going up a little bit, but then eventually it's going to slump. And the height of the release basically will affect where you have your maximum concentration, at what distance, right? But the maximum concentration would be here, would be lower than if the release was on the ground, right? And then of course, if you have a release initially, it depends on, right, if it might come out hot, it's gonna be lighter than air, but it's gonna cool down, and eventually we're gonna reach where it's dominant by the ambient turbulence. And basically, we're gonna assume, what we're gonna look at is only neutral buoyancy, what we have. So we're not gonna complicate things further, right? We're gonna take it down here because that's where the community is, and assume that at that point we're dominated by ambient turbulence, and we have a neutrally buoyant model that we can use. Okay, so if you look in chapter 5, there are a lot of different case studies, right? That they have put up, and we're gonna basically ignore the first 10 or 11. Okay, we're just gonna skip them, because if we look at them, they've set up equations for all this. If we look at the how the concentration changes with time, right? At time and a distance. This is you assuming neutral buoyancy, but we have these eddy diffusivity, which would be necessary for us to determine because of the turbulent flux. Okay, and that is complex and difficult even for the simplest case. So we're going to sort of cheat because it's not that, you know, this is not a mathematics course or anything, right? We need to use something easy that we can handle a lot easier. So instead, we're going to use dispersion coefficients. So basically, it's standard deviations that we're going to deal with. Did you have a question?
Yeah. Is eddy a name, or is that like a word for something?
You know, it might just be eddy diffusivity, like you eddies on the, right? You know, like the eddy
like
current.
I think that's what it is.
That's what it's
Okay.
refers to.
Never heard of it.
But I was gonna say, but you don't have to worry about that, because we're gonna ignore all the first 10 or 11 cases where they deal with that and how to solve it.
Yeah.
We want something that's convenient and easy to use. So the equations may look a little scary, and it just takes a little while to get used to, but it's a whole lot easier than trying to solve, you know, a number of differential equations. So we're just going to use dispersion coefficients that are, you know, functions of distance downwind, and it's basically standard deviation. So it's like, what's the width of the concentration, right? But we're gonna look at it. The dispersion coefficients are going to be different whether we're going downwind, crosswind, or up and down. And what we're going to use is this Pascal-Gifford dispersion model, which, again, there are 4 different equations. We're going to look at, this is for, I couldn't find my laser pointer. Can you see the little arrow here? So we're going to have 4 cases again. We're going to differentiate between continuous release, so that's a plume that forms, right? A plume that forms downwind, or a puff, where you might have an explosion and you have a release of a cloud of material that is transported downwind. And then we're going to look at whether it's done at ground level or at a height. But this is basically, so what we have is the concentration for a continuous release in this case is of course dependent on what the mass release rate is from that continuous source. Okay, this is only at ground level. It's dependent on the wind velocity, which comes in here, and then these dispersion coefficients. So remember, there are standard deviations that we'll put in. They come in here as well as in this. So Y is now, X is always downwind. Okay, so that's where the wind's blowing, that's where the concentration is going to be highest. Y is crosswind, so that's right, you know, in your coordinate system, and C is up and down. So in other words, if we have these dispersion coefficients, then if we know the release, we can calculate what the concentration will be, I don't know, 200 meter downwind 200 meter downwind, 100 meter crosswind, up and down, you know. Basically wherever we know we have a high density of population, right? And those dispersion coefficients, here's how we're gonna take into account the atmospheric conditions, right? They're dependent on the distance downwind and the atmospheric conditions. And we're gonna look at atmospheric stability. And we're gonna differentiate. There are equations for these two, so you don't have to read log graphs. But if we plot it, so if we plot the sigma x is equal to sigma y, but if we plot it as a function of the sigma yx versus distance downwind, this is what it looks like for different atmospheric stabilities. So we're going to have A, B, C, D, E, and F. And if you remember the equation that we were looking at, worst case here, the highest concentration we get when these are as small as possible, right? So atmospheric condition F, in other words, would be the worst case. That would give us the highest concentration. We have two sets of these. This is for a rural release. So this is in a rural community. There's not a lot of buildings. Okay, so what does that mean? That means that the concentration will be higher because we don't have the same degree of vertical mixing. The other thing we have is fewer people than if we are in a city with high rises where we have vertical mixing and potentially a smaller concentration, but a lot more people that are affected. So obviously we need to take all of those into consideration. That's the equation for sigma z. These are the same, but for an urban release now. So there are two cases here, basically. And those A, B, C, D, and F. This is basically how we determine that. It's the atmospheric stability, and it's dependent on whether it's daytime or nighttime, and what the wind speed is. So if you saw in that, F was always at the lowest, the smallest value. So for F condition, that happens at nighttime when we have that temperature inversion, and nighttime and small, low speed, low wind speeds. And it says less than 2. When we do calculations and you're looking at worst case scenario, I would just assume like a wind speed of 1 meter per second, for example. It's also interesting to note though, right, that this would be the best. This has the, A is the extremely unstable. So that's what happens when you have the sun is shining and it's hot and you have a lot of vertical mixing. So when you have a lot of vertical mixing, you don't want that wind speed to carry it, right? See that? So this is the best scenario A. That's what we want, to dilute it as much as possible. F is the worst. Okay, so that's things. And if you have to decide on these, you're going to get some cases, right? It's either nighttime or daytime with a certain wind speed. And we can go in here, and then instead of reading the log graph, I did not put the equations in there. There are tables with equations to use that I would say is easier to use. Okay, but the one we were just looking at, the equation I put up there was for continuous release, right, at ground level, but we're going to look at puff in plume, so a continuous versus an instantaneous release, and ground level versus height. So there are four cases. Let me see, case 12. So we're just ignoring case 1 through 11. Okay, we're going straight to 12. This is what we're going to use. So this was the continuous release. That was the plume that we were just looking at. So we need the mass flow rate, right, of the release, which is perhaps what you calculated from your gas leaking or an evaporation rate from a pool of liquid, right? This is the ground level one, and it describes the concentration as a function of distance, right? The only thing to keep in mind is that the wind velocity is in the x direction. That's always the case. Okay, this is just the, these are